Welcome to Mastery Learning. You're going to use these videos to help you understand what the lesson is all about. Then you're going to come into class and we'll go over any questions that you might have. So, please make sure that you have a pencil and paper handy so that you can put this information right into your math notebook. Remember, you can stop this at any time, pause, write down your question, and then start it up again. We'll go over everything in class, but we'll do it in small groups. Okay, so what are we going to do in this lesson? We're going to talk about rational numbers. You know this from previous studies. Rational, of course, comes from ratio, and here we're talking about the ratio of one integer to another integer, such as 1 to 3, and it can be expressed as a fraction. This would be a rational number. How do you distinguish between a rational and an irrational number? What it really comes down to is if it can be expressed as the ratio of two integers, it's a rational number. And if it cannot be expressed as the ratio of two integers, then it is an irrational number. Adding positive and negative numbers, boy, that probably sounds really too simple, doesn't it? But somehow we can get so confused when we are trying to subtract a negative number. When we are subtracting a negative number, of course, it is the same as just adding it. And if we are adding a negative number, it's the same as just subtracting it. Subtracting positive and negative numbers and using real numbers in solving problems. Let's take a look at this little cartoon I borrowed for us for today. We have no such rights here, do we? Or do we want to be? Okay, so we're going to get going on this. This is a Venn diagram. You saw these probably in earlier courses. What we see here is all of complex numbers. That's the whole of this. Within all complex numbers, we have something called imaginary numbers that we will study later. Actually, we'll study this in the second semester. And we have this, which you've been looking at for years now, real numbers. Real numbers include the rational and the irrational. And we just were talking about how you can tell the difference between them. There are other ways that we might categorize numbers. We could say about real numbers that we could talk about whether they're negative or positive. By the way, 0, it is a real number. It's neither negative nor positive. We could look at the digits in terms of whether they are odd or even. So those are just other ways that we could categorize real numbers. What you want to remember for right now, rational and irrational. All real numbers are either rational or they're irrational. Real numbers and the real number line. So a real number line will contain rational and irrational numbers. Let's take a look at this. Will there be always be a rational number between any two rational numbers. What do you think? Let's say I'm looking at 1 and 2. Could I find a rational number between those? Right? Let's say midway. Well, you might say 1 and 1/2 would do it. Right? We could write it as 1.5. That would be a rational number. Why do I call it a rational number? That can be expressed as an integer over an integer. Yes, that would be 3 over 2. Now, if you're wondering how to quickly determine whether or not it can be expressed as the ratio of two integers, think about this. If I were to just move this is a terminating number. It doesn't go on and on. It just stops right here at 0.5. If I were to multiply that by 10, I'd have 15 over 10 would be equivalent to it, right? And we can see right off that that is a rational number. It's the ratio of an integer to an integer. So, answer? Yes. If you were to remove all rational numbers from the number line, would there be any numbers left? Well, since we're not talking about a rational number line, we're talking about a real number line, and we know that contains both the rational ones, such as this one we're looking at here, and the irrational numbers. Yeah, if I took all the rational ones out, I would still have numbers left. Those would be the irrational ones. Okay, so let's take a look at this and determine whether we've got rational or irrational numbers. Now right off I'm looking at something which isn't all that easy to interpret. I do know that it goes on and on and on because I see these little dots. And you probably notice we've got a pattern here that keeps repeating. Whenever you see a repeating pattern exactly the same, 1 9 1 9 1 9 1 9, could be more than 2 in the repeat, we know that this actually is a rational number. So this is rational. So you look for that repeating, remember that from Algebra 1, look for that repeating decimal pattern. That's a signal that it is a rational number. Let's look at this one. We see some kind of pattern going on here. I've got 0 1 1, 0 0 0 1 1 1 1. Oh, well, there's some kind of pattern going on, but it's not staying the same. It's morphing each time. So we would say this is an irrational number. It does not have the same pattern repeating again and again. How about this one? Well, there's no sign that this is going on and on. We know we could write this as 8 7 1 4 over 1,000. This is rational. A rational number. The square root of 5. We might try that on your calculator right now and see what you get. See any pattern there? There's no repeating pattern in your decimals. This is an irrational number. Do not think that all square roots are necessarily irrational. Let me give you an example of one which is very rational. The square root of 4. Now it's disguising itself as something that you might stop and wonder about, but what is the square root of 4? And of course, that can be expressed as a ratio of an integer to an integer. So that would be a square root, which is actually a rational number. But very often, let's think about it this way. Once you have simplified it as far as it can go, you are talking about an irrational number when you look at square roots. But remember what I said, after you have simplified it. Absolute value. You've studied this before. What does it mean, absolute value? It means you talk about the distance, but you don't talk about the direction. So negatives get stripped out of it. For example, if I had the absolute value of -3, that's talking about what is the distance of -3 from 0. So here it is. We're going 1, 2, here it is, right here. That's -3. How far is that from 0? If we disregard direction, which absolute value does, we're talking about 3 units. This is 3 units away from 0. Absolute value will strip off the negative of whatever expression we have here. So I'm going to add some real numbers. I'm going to add -2 and -7. What's going to happen here? They have the same sign, so I'm going to sum them. And what is the sign of my sum going to be? Yes, negative. How about this one? I'm going to add a +32 and a -6. Whenever the signs are different, here's a negative, here's a positive, we look at the difference between them. What is the difference between these two? 22, you say? What sign am I going to use? I'll use the sign of whichever of these is the larger. 32 is definitely larger, and it is positive, so there's my answer. How about this one? I have a negative and a positive, so I'm going to look for the difference between them. What is the difference between them? 0.3. And 1. And the sign I'm going to use? The sign of the larger one, which is negative. How about this one? Now, this one's gotten a lot more complicated because these are considered unlike terms. You cannot add unlike terms. I cannot add thirds and sixths. They're different. So let's make them the same without changing the value of this. How can I convert this into sixths? I can multiply it by 1. We know 1 doesn't change the value of anything. Multiplying by 1 is the identity. It keeps things the same. It's going to look different, though, because it's now going to be -10 over 6 plus 1/6. Now, we're going to use our rules for addition of negatives. If you have a positive and a negative, you're going to find the difference, and that's going to be 9/6. And what is the sign going to be? The larger. A -10 is certainly greater. Well, a 10 is greater than 1, so we end up with -9/6. Now you can see that you would not leave that like that. That could be simplified to -3/2. Right. Let's look at these rules. To add when there are like signs. Add the absolute values. When the signs are alike, add the absolute values. The sum has the same sign as the addends. Those are the components. So for example, over here we had a -12 and a -7. These are like signs. The absolute value here is 12. The absolute value here, 7. Add them together, you get 19. The sum has the same sign as each of these components. They were both negative, so the sum is going to be -19. Okay. To add when there are unlike signs. So we take the difference between those absolute values, and the sum has a sign of the addend with the greater absolute value. So in this case, 32 is one of the addends, and -6 is one of the others. The greater was positive, so we had a positive response. This one, the greater one was negative, so the difference was negative. There's not really anything new there other than maybe a little bit of vocabulary. An addend. Chances are you've seen that before, but it would be the kind of thing I would have forgotten. I don't know about you. Subtraction of real numbers. What's the additive inverse of -1/2? There's a lot of new words here. Additive inverse. We're going to use additive inverses as a way of subtracting by adding. An opposite will undo the operation. The opposite of adding is, that's right, subtracting. We can use the additive inverse. What in the world is the additive inverse? To subtract, you're going to add. And what do you add? Well, in order to make this work, you have to add the opposite sign. So let's look at this one. This you're supposed to be subtracting, but we are going to convert it into adding. So we're going to say 7 plus a -10. We'll find the difference between them, which is 3. Take the sign of the larger one, -3. Let's go back up here and talk about additive inverses for a moment. What would be the additive inverse of -1/2? The only thing that's going to change with an additive inverse is its sign. If we were talking about a multiplicative inverse, then we would take the reciprocal. But this is not multiplicative, this is additive. So the only thing that's changing is the sign. This is going to be a plus 1/2. Here's a tricky one. What's the additive inverse of 0? Well, didn't we just say that 0 is neither plus or minus? So the additive inverse of 0 is 0. Okay, so let's go through a couple little exercises here. We want to convert this into an additive inverse. So that would be 8 plus a negative of negative 5. That seems unduly complicated. What is the negative of a negative? Certainly 8 plus 5. The answer to this one, of course, is 13. How about this one? Rather than subtracting, we're going to add, so we're going to have a negative 3.8. And to that, we're going to add the additive inverse of a positive 4.1. So that's going to be a negative 4.1 is the additive inverse. And what happens here? These are both the same sign, so we add the absolute values together. And what do we get? 9, that's right, and 7. And the sign, of course, is going to be the sign which both addends had. Finally, let's convert this into an addition problem. We've got negative 7 over 2. And we're going to turn this into an addition problem. If we're subtracting a negative, it is already an addition, right? So we could just write this as 4 over 5. Now, it is a little complicated, isn't it? Because these halves and these fifths are unlike. What do we have to do? Find a common denominator. What is the common denominator here? It would be 10. So the least common denominator we find for this problem is 10, which means I have got to multiply this by a 1. Remember, we can multiply anything by 1. It will not change its value. Plus, we've got 4/5. To get a common denominator of 10, this has to be multiplied by a 1, which looks quite different, but it's still equal to 1. I will end up with a negative 35 plus 8 all over 10. I should think now, what will that be? I'll find the difference between the two of these, which is 27 tenths. And the sign will be the sign of the larger. So there's my answer. Multiplication and division of real numbers. Multiplication has different rules. In some ways, it's much easier than adding and subtracting. Certainly when you look at fractions, it seems easier. Dividing positive and negative numbers. And, oh, this is such a biggie, recognizing that you may not divide anything. Here's anything. No! You may not divide by 0. Let's look at the little cartoon for us here. Now that's a very good reason, right? I had to learn this, so now you do too. Well, in some ways it does seem like that because we don't know. what are we going to do with this? Of course, that's the point. You may need it. You may not think you need it, but it's part of the basic language of mathematics. And we're in high school, so we ought to make sure we know the basics. Multiplication of real numbers. 2 times 5. How about 2 times a negative 5? One times 5. How about 1 times a negative 5? 0 times 5. That's right. Anything you multiply by 0 is 0. So whether it's negative or positive, multiplying by 0, you get 0 for your answer. Please notice up here, too, when you're multiplying by 1, that's the identity factor, nothing changes. It stays the same. How about multiplying by negative 1? Well, that certainly changes things. The absolute value stays the same, but the sign changes. Over here, where I had a negative and now I'm multiplying it by another negative, what happens? That's right. That's positive. If you have a negative times a negative, you get a positive result. Negative times a positive, this is going to be a negative 10. A negative 2 times a negative 5, going to be a positive 10. It's kind of interesting, isn't it? You've gone from 10, 5, 0, negative 5, negative 10, and over on this side where you were working with a negative to start with, you start with negative numbers and proceed up through 0 and into positive numbers, multiplication of real numbers. Multiplication and division of real numbers. What are the rules for the sign of the product? If the numbers are both positive or both negative, what are we talking about there? They both are the same, or they both have the same sign. Their product is positive. However, if you have two numbers, one is positive and the other is negative, these are factors which have different signs. Another way to say it is that if numbers have an odd number of signs, of negatives. If numbers have odd number of negative factors, because we could have many, many factors, couldn't we? Then your product is negative. Okay? So that's another way you could say it. All right, let's check our understanding here, see if we know what we're talking about. Does negative 3 times negative 3 equal a positive 3 times a positive 3? Well, let's check it out. Negative times negative, we're just going to do this side right now. That would be a positive 9. Now, does that equal 3 times 3? Certainly does. Negative 3 times 0, does that equal positive 3 times 0? Anything multiplied by a 0 is 0. So we've got 0 over here, and we've got 0 on the right, so the answer there is yes. does 1 times a negative 1 equal negative 1 times 1? Well, this has got two factors with different signs, so their product is going to be negative 1. Same thing here. Two factors with different signs, negative 1. So in all of these cases, these are equal to one another. The reason why this is true, all we've done here is we've swapped positions. Do you remember what that property is called? The commutative property. We'll be coming back and talking more about the commutative property. If you're trying to remember that word, which I think is really hard to remember, pick up on these first two syllables and think of commute. I didn't even spell it right, did I? Well, anyway, commute. If we commute from position 1 to position 2, and this one from position 2 to position 1, with multiplication, nothing changes. The result of that multiplication doesn't change. Not everything is commutative, and we'll talk about that later. But addition is, and multiplication is. Okay, so let's try multiplying these. What would this turn out to be? Well, this is going to be 99, and the sign, because we have different, this one's a positive, this one's a negative, it's going to be a negative 99. How about this one? That's right, this one will be positive. They have the same sign, so, and there's just two of them, so it's an even number of negative factors that'll always be positive. So that'll be a positive 28. Here we have 3 negatives. Ooh, right, 3. That's an odd number of negatives. So the product will end up being negative. 1 times 1 times 1. Don't you love 1? It's so easy to work with. Multiplication and division of real numbers. Here we're going to talk about what would be the opposite operation. Remember, in addition, the opposite of addition, I don't know if that's the legal kind of way to write it, is subtraction. And we could write it the other way too, that the opposite of subtraction is addition. Well, when we talk about an opposite operation, one that will undo that operation, in the case of multiplication, what is the opposite of multiplication? Division, right? Another way to look at it is the opposite of multiply is to use the multiplicative inverse. Woo! What's that? You probably know it as the reciprocal. There's a lot of vocabulary you're going to be encountering here in Algebra 2, and you should make sure you keep some notes on that. There is a way in which you can convert every division problem into multiplication. It definitely has its advantages to do that too. So you can change any division by multiplying by the multiplicative inverse or the reciprocal. Any time that you undo multiplication, you will get back to 1. So if you think you're undoing the operation and you don't get a result of 1, you haven't undone the multiplication. Okay, let's go up here and look at reciprocals for a minute. Is negative 3/4 the reciprocal of 4/3? Well, not quite, right? Because we're not doing anything, we're not talking about the additive inverse, which would change the sign. We're talking about the multiplicative inverse, which simply takes the reciprocal, doesn't do anything with the sign. So if that weren't there, we could say yes. How about this one? Is 3/-4 the reciprocal of -4/3? Certainly is. See how simple that is. We don't want to add in any negatives, but if we already had a negative, it stays. Divide by multiplying. All right, so how are we going to do that? We're going to say, oh, that's a bad sign for me to use. Let's do this. That's the same as saying 24 times, instead of divided by 3, times, oh, I want to do it even differently. We could write this as, let me do it as -24 divided by 3. And I want to change it into multiplication. So I can write -24 times the reciprocal of 3, 1/3. All of these represent exactly the same number, which is what? Negative, I didn't leave myself much room, -8. Let's do the same thing here. We have a -15, which we are dividing by a -3. That's the same as -15 multiplied by the reciprocal of -3, which would be -1/3. Two negatives multiplied together will be positive, and 15 times 1/3 will give us, that's right, a 5. Let's try this one. Here it's already written as a division. Now, hint, if we were adding and subtracting, we'd be in trouble right now because we wouldn't have like numbers. This is very nice about multiplication. We don't have to have like numbers for multiplication. With multiplication, we just multiply the numerators together and multiply the denominators together. Of course, this isn't multiplication, is it? Oops! This is division, and I don't want to divide. I like multiplication so much better. So what do? You maybe remember this from elementary school. Stay, change your operation, flip. So that's what we're talking about in here. When we talk about using the multiplicative inverse, we're talking about that old stay, change the operation, flip. So we flip the thing we're dividing by, and now we can do that very simple operation in multiplication of fractions. We multiply the numerators together, we get 14. We multiply the denominators together, we get 45. I love it. Okay, this one isn't all that much different, is it? It's just now we've got a negative to deal with. We know how to deal with a negative. We'll talk about that. So I've got 4/5. It's my stay. Then I'm going to change from division to multiplication. And this time I'm not putting that multiplication sign in. We know if we see two fractions side by side like this, with one in parentheses here, we're talking about multiplication. And that's going to be a negative. Well, that didn't show up very well. Negative. Oh! Now I want the reciprocal. See how easily you can get sucked into doing the wrong thing. I want the reciprocal. It's stay, change, flip. I wouldn't get the right answer if I didn't flip. So now I know I've got one factor which is negative and one factor which is positive. Two factors where they have different signs, the result is going to be negative. I'm going to multiply the 4 times the 11. And the 5 times the 6. Now you tell me, would you leave that answer like that? You should always look to see if you have a common factor. This, I could factor a 2 out of it, couldn't I? It would be negative 22 times 2. This I could factor a 2 out of. 15 times 2, so I'd end up with negative 22 over 15. That would be the best way to express this answer. This would be fully simplified. This would be 100%. With me, if you leave it here, and we're just doing such a simple operation, that's probably a B, and this one is an A. So it's worth taking a moment to see whether or not you can simplify. Division by 0. We all know, don't we? We all know that we can't do that. I hope we know that. Division by 0. No! There is no reciprocal for 0. There's no multiplicative inverse for 0. You may not divide by 0. Okay. Let's try it on your calculator. So you're going to love this. I actually have a little calculator we can bring in here. First of all, get your calculator. Oh, I should have mentioned it earlier. Pause this and go get it. Let's try it. We're going to say 0 divided by 1. What will that be equal to? 0. Now we're going to try 1 divided by 0. What do you expect is going to happen now? We know that this is an illegal operation, don't we? We cannot do that. Error, it says. You're dividing by 0. Quit. All right, we'll quit that. So, the reciprocal of 0, there is no reciprocal of 0. Can't do it. Well, let's test our understanding. Which of the following divisions are possible? Let's look at this. This is the same as 6 over. What are the rules here? This is where you want to remember PEMDAS, right? Please excuse my dear Aunt Sally. We always do what's in parentheses first. We don't have anything in parentheses. Then we do exponents. We don't have any exponents. Then we multiply. Well, we do have multiplication here. So it's going to be 6 minus 6. Now, because this is in the denominator, we probably should be looking at it like this and go back here and say, okay, we better take care of our denominator first, and we'll have 6 divided by 0, which is what? Not allowed. So that's not possible. How about this one? I'm going to look at this as being parentheses. That's just what I should have done up here. So I have to handle what's in parentheses, and then minus what's in parentheses. I've got 2 squared, so I have to take care of my exponent first. I'm going to have 4 minus 4 over 8. This will become 0 divided by 8. That one's a possible, isn't it? Of course. How about this one? Now, at first glance, I know when I first looked at this, I saw this is the same as this. And I know a rule for when things are the same. If I have a fraction where the denominator and the numerator and the denominator are the same, that would be a 1. Oops, with one exception, and this is it. If your denominator becomes 0, which it does, then that does not equal 1. This is not allowed. We cannot make that division. Ooh, that was really good exercise. We'll work on this next time we get together. See you back in class.